So homework number 2 is going to be due on Thursday. And I also wanted to mention that I've uploaded a sample midterm exam and the exam equation sheet to Blackboard. And I guess I just had Blackboard up. I can show you again where you can find those. In case you just want to see, like, if you want to see like what kind of an exam you ought to expect from me, then you can find it. It's right here is the sample exam, and you click on that, then you'll just get an idea of typical, what's a doctor weight exam look like, and like level of difficulty for the type of material that you've had and so on. Likewise, you can find the equation sheet, and these are the formulas that, if we have an in-person exam, then I wouldn't allow you to use the books and previous assignments and stuff. And the exam conditions will be a little bit different this semester because of the remote learning that we're doing. But we'll get into those details. I just wanted to let you know that both of those resources are available now on Blackboard. All right. So today we're going to continue talking about hydrostatics. We've already talked about the hydrostatic equation, and we're going to continue on and see where it leads us, the different types of applications that we can use with the hydrostatic equation. Before we get into pressure transmission, though, I wanted to spend a few minutes talking about some key ideas from homework problem number 2, and this is on the assignment that's due on Thursday. And so the setup here is that at the base of a mountain where it is sea level, we know atmospheric pressure, and we know that water boils at 100 degrees Celsius down at that atmospheric pressure. And so the problem suggests, what if there is a mountain that has an elevation of 4,100 meters? First of all, what's the pressure up at that elevated location? And then once you find the pressure, what is the boiling temperature for water? And so the problem says that in this case you can use the unit weight of air of 11.8 newtons per meter cubed. And just like the hydrostatic equation can be used for liquids, the hydrostatic equation can also be used for gases. And so what you can use is this formula for delta P. And starting at sea level, where we know what the pressure is, you can find the pressure of the atmosphere up above at an elevation of 4,100 meters. And so the pressure is going to be lower. That's why people struggle to breathe, when they go up in mountains. It's not that the percentage of oxygen is any different, because it's not. The percentage of oxygen and the percentage of nitrogen, they stay about the same. What makes it more difficult to breathe is that the pressure is lower. And so you'll find that reduced pressure up above, and then you can use this relationship to find out how the water temperature, that the boiling temperature for water is different. Now this is slightly different from the way I've described it, and in the handout I put a negative sign. And the idea with that negative sign was that I wanted to make it clear that at that higher elevation that there's going to be a reduction in the boiling point of water. But I guess if I'm going to describe this as the relationship between water temperature and vapor pressure, then maybe that negative sign isn't helpful, because what we know is that at the higher elevation, the pressure will be lower and the boiling temperature will be lower. So you can use this relationship, and if you flip it, if you find the inverse, then it's going to tell you what is the delta T for a certain delta P. So I don't want to say too much beyond that. I think I've given you some pretty solid clues here. I want you to continue to think through it a bit further, but what we're just trying to do is predict the boiling temperature for water. And we've already talked about that in the previous lecture, that we know it's going to be less than 100 degrees Celsius. Just the question is, at what temperature specifically? So if you get that it's boiling at a higher temperature than 100 degrees Celsius, then you'll know that that you need to continue working on that. And so hopefully this clarification will provide you a little bit of direction on that problem. All right. So let's briefly review where we left off last time. We saw the full hydrostatic equation, as it was called, and then an abbreviated version of the hydrostatic equation. And so here in the figure on the left, it's saying that we have a 50-meter column of water. There's just, let's call it a tank. And up at the surface of that tank, it's open to the atmosphere. Now, there is some symbology here and a convention that I need to address. It's typical in fluid mechanics texts for this triangle on top of the water. You can see the triangle there. It kind of indicates that it's in contact with the atmosphere. And so that's a clue that this tank isn't sealed, but rather it's vented just to whatever pressure is existing at the air above that. And another similar clue is this line down below the triangle. That line is meant to kind of bring to mind the rippling of water. Sometimes there'll be more than one. Sometimes they'll be dashed, and 3 or 4 of those lines just means that that's a free surface of water up at the top. So what we can take from that is P1 is 0 in gauge terms. P1 in absolute terms is going to be 101,325 newtons per meter squared. So what I'd like you to do is just to refresh your memory on how to use the hydrostatic equation, and have you memorized the unit weight for water yet? If you haven't, it's just right around the corner that you're going to start to be able to recall some of these fluid properties without having to refer to a text or being told. And so by unit weight, of course, I mean gamma. And so the unit weight of water, if no temperature is specified, like in this example, it just says water, then you use the default assumption that the unit weight is 9810 newtons per meter cubed. All right, so let me pause for just a moment. Try using both of these equations to find out down here at location 2 what is both the absolute and the gauge pressure of the water. All right, let's just see if we're both thinking the same thing. So if we use the full version of the hydrostatic equation, what we're going to say is P1 is 0, because that's the working first with the gauge, let's say. So P1 is 0, Z1 is 50, if we're going to use the bottom of that tank as the elevation datum. And so P2 is the unknown, and Z2 is going to be 15. All right, so let me pull up the solution, bring it over here onto the screen. All right, so just defining some variables here. Z1 is 50, Z2 is 15, P1 is 0 gauge. And so in absolute terms, then that's 101,325 pascals. And so here we have both the gauge and the absolute pressure at location 2. And you can see that I first, before starting to substitute in the numbers, rearranged things symbolically. And so saying that the pressure at location 2 is going to be, like what's causing that pressure? Well, what's causing that is the weight of the water, well, the amount of water above it, the distance of water above it. And so you can see when I've rearranged this symbolically, we've got the Z1 minus Z2 multiplied by the unit weight gamma. So that's kind of like the delta P formula when we use the abbreviated version of the hydrostatic equation. And so in gauge terms, that's where we assume that P1 is 0. But if we want to find the absolute pressure at 2, then we just put in whatever the pressure at location 1 is. And assuming that it's at sea level, then it would be 101,325. Okay, so this is the full version of the hydrostatic equation. For abbreviated, we'll get the same answer, but the application is just that we're going down through the water. So the delta H is talking about how far deep below the water surface is this location of interest. So that's 35 meters. And the unit weight of water is the rate at which pressure is accumulating. So if you think about these units, newtons per meter cubed, another way of thinking about those units is it's newtons per meter squared per meter. So that's 9810 pascals of pressure increases for every meter down through the water that you go. And we're going 35. So that means that the gauge pressure is 343,350, and therefore the absolute pressure will just be that gauge pressure plus atmospheric. All right, so that refreshes our memory after a long weekend how to use the hydrostatic equation. Now there's some interesting applications of that. One is that if we had a water fountain connected directly to a dam and we knew the elevation of the water behind the dam and the elevation of the fountain, then we could use the hydrostatic equation to find what is the pressure in the fountain. So let's just, for kicks, find out the pressure in the fountain. And we're going to assume, of course, that the air that's in contact with the water has no pressure. So in part A, when it says, what's the pressure in the water fountain, it's kind of implied that we want to know the gauge pressure. So what's the pressure over and above atmospheric? So find the gauge pressure of the water in the fountain. And then you can see in part B and C, we kind of pose a what if. What if the fountain can tolerate under 850 kilopascals? And that's a pretty typical maximum limit for like municipal water systems and for domestic fittings. 850 kilopascal is sometimes considered like an upper limit of what you may want to have in something like this. So if the pressure can be 850, then how high can the water surface elevation be? And then part C is just kind of a concept question. So I'm going to pause again and ask you to calculate part A and part B, and then we'll discuss what's going on with part C together. Okay, so how are we going to find the pressure in the fountain? Well, we're just applying the hydrostatic equation again. So the elevation difference between the 615.47 meter water surface and the elevation of the fountain, so the delta H is 27.11 meters, which means the pressure change is going to be 265.949 kilopascals. And just, for reference, a typical, I told you that 850 is kind of at the upper limit of what would be acceptable in your municipal network. Kind of the lower limit for what people are going to like in terms of the pressure in their fittings would maybe be about 240 kilopascals. So this is just barely enough pressure that the water is going to flow well through that fountain. All right, part B asked if the pressure can be 850, then what's the maximum elevation? So is it going to be higher or lower than what's described now? If this fountain can tolerate 850, and right now it's only at 265, that means that we can have a much bigger delta H if needed. The water level behind a dam often fluctuates by quite a lot over the course of an annual season. And so in part B, what it's doing is it's just saying how high can that water level go and still cause an acceptable pressure. And so if we have a maximum allowable of 850 kilopascals, and that tells us then the delta H max, and the most the water level can be above that fountain is 86.65 meters. All right, so that means in absolute terms, relative to whatever this datum is that we're measuring, I guess it's probably sea level, and that means that the water surface can go up to 675 meters. Any questions about these first parts of the question? All right, well now what about the theory though? What effect would a longer pipe have on the static pressure? Anyone willing to venture a guess and comment on, in this situation, is a short pipe versus a long pipe? So we see, let's say that right now it's 100 meters long. What if it switched from 100 meters to 1,000 meters? What effect would that have on the pressure? Anyone? Certainly, 1 out of 32 is willing to take a guess.
I don't think it would have an effect.
You're right. Why do you say that, Cole? Why is it that it wouldn't have an effect?
Because the only variables that we have for this are the difference in height. So as long as the pipe gets the fluid connected, it doesn't matter how long it is. It's just about its height.
That's exactly right. Yeah. And I kind of emphasized that or gave a clue when I referred to it as the static pressure. Static means that the fluid isn't flowing. And so as long as the fluid isn't flowing, then the pressure in the fountain only depends on the height of the water behind it. But if we started to draw water from the fountain, then the pressure is affected by more than just the hydrostatic equation. And so hydrostatics means water that's not moving. And this hydrostatic equation only applies for fluids that are at rest. If water is flowing through a river, then the hydrostatic equation isn't going to exactly describe the pressure elevation profile. If water is flowing through a pipe, then there's going to be huge variation between what the hydrostatic equation predicts and the actual pressure. So when we get a little bit further in the course, chapter 7, we start talking about water flowing through a pipe and how frictional effects will change the pressure that we'll see. But for now, it's exactly right that making the pipe longer isn't going to affect the pressure. Okay, so here's another application of these ideas of the hydrostatic equation. It's just a schematic diagram here taken from the textbook of an automobile lift. And the way that this lift operates is that compressed air goes from the compressor into a chamber, and you can see that there's some air acting on top of the oil. And the purpose for that is that the air is pushing down on the oil because the pressure acts in all directions. And so if we have a horizontal surface, this interface of the air and the oil, then the pressure is going to be acting down upon that interface. And so now the oil is pressurized because the air above it is pressurized. And so, just for instance, if it's pressurized to 600 kilopascals, if the air is, then that means suddenly the oil is pressurized to 600 kilopascals. And of course, the hydrostatic equation tells us that if we go down through a fluid, so if it's 600 kilopascals at the interface between the air and the water, and then we go further down through the oil, then the pressure increases. And then when we go sideways, the pressure doesn't change. So if you go sideways through a fluid, the pressure is the same. And if you go up through a fluid, the pressure decreases. And so these two interfaces, the interface of the air and the oil, and the interface between the oil and this steel, I guess it's like a lift plunger or something like that. This big steel part here, they're at roughly the same elevation. And so the oil pressure is the same in both of those locations. by the way, I'm noticing that I think the mouse cursor that you see might be in a slightly different location from the mouse cursor that I see. So like, for instance, right now, is it pointing to 25 or is it pointing to the concrete? Is it like right next to the 5, what you see? Now
It's on 25.
All right, so it's right next to the 5 right now. Oh wait, right there. Is that on the 5?
Yes.
Okay, that's so funny. Last semester, you couldn't see the cursor at all. Now you can, but it's in a slightly different location from where I see it on my main screen. So I'm going to have to, when I point things out, I'm going to have to look at my secondary screen and do it that way. But all right, so thank you. The key idea that we need to start with is that the pressure of the air and the oil is the same everywhere along this boundary. And also, the pressure of the oil is still that same thing on this boundary. And so the air was pushing down on the oil from above, and the oil is pushing up on that steel cylinder from beneath. So in this example, the pressure that's produced inside the compressor can be transmitted to this oil over here. Pressure transmission means that the work is being done in the compressor, but the place that effect is being exerted is the oil pushing up on the steel cylinder that lifts the vehicle. And so remember that force can be calculated by multiplying a pressure by an area over which it acts. And so if you think about the units there, pressure has units of Newton per meter squared, area has units of meters, and so the force acting upward on the vehicle is going to be in newtons, because what we're going to do is we're going to integrate the pressure over an area. And so let's put some specific numbers to this. What if the diameter of the cylinder, as it says here, if it's 25 centimeters, then we can find the cross-sectional area of the cylinder. I've just done the calculations for you. Area is pi d squared divided by 4. And so if you have a diameter of 0.25 meters, square that, multiply it by pi, divide by 4, so the area is 0.04909 meters squared. So what force will be lifting up the car if we have this area and this pressure? So if you just have your calculator handy, you can do that and see that okay. You can see in the sketch that I've kind of indicated that the air is pushing down on the oil, and then that effect is that the oil pushes up on the steel. And the magnitude of the pressure is the same, even though the surface area that the air was acting on is different from the surface area that the oil is acting on. And so if we go back to the original image, okay, they don't tell us the diameter of this oil-air interface, but they don't have to. All we need to know is the diameter of the steel cylinder that's being lifted up. And so if you multiply the pressure over the area by which it acts, then you can find that it's able to lift a force of 29.4 kilonewtons. And just for perspective, that's about 3,000 kilograms of mass. And so 3,000 kilograms of mass is going to be about 7,000 pounds, since there's 2.2 pounds per kilogram. So it can lift something very, very heavy as long as we've got a compressor that can get up to 600 kilopascals. Now, concept questions. Go ahead. Does somebody have a question?
Yeah, sorry. So if the oil height and the air height, like the line on both of them wasn't uniform. I guess that has to be because that's how liquids work. But if it wasn't for some reason,
Yeah, good question. Yeah, so your question is, what do you do then if it's not at the same elevation?
yeah,
You use the hydrostatic equation to find out what is the pressure at the interface of the oil and the steel. So for example, if we turn the air compressor on so that now there's more than 600 kilopascals, it's going to lift the car up higher. We kind of already know that it's going to lift the car up higher if we turn the compressor on. Like, let's say right now it's in equilibrium, the compressor's off, it's at 600. So we pressurize it further, that's going to lift up the car. And so that means if the car is higher, then the oil is going to now be up here. You know, it's going to be some distance higher. And the way that it's able to do that is that there's going to be more pressure inside the air component. And so you just use the hydrostatic equation to find the new pressure at a certain elevation.
okay, thanks.
Yeah, we'll do examples like that. Here's another kind of what if. What if instead of a 25 centimeter diameter cylinder, what if we had a 50 centimeter diameter cylinder? Then how much could it lift if we doubled the diameter? You need to be careful. There's two different things going on here, but try and think. If you double the diameter of the cylinder from 25 to 50, what does that do with the force? And let's say that it's still at the same elevation. KC guesses it would lift half as much. That's not a bad guess, but it's not the correct answer. So think about from the formula. Okay, Peter guesses that it's going to lift more. You're in the right direction. How much more? How much more can it lift? So think about pressure is the same in this formula. If you double the diameter, what do you do to the area? And area is pi d squared divided by 4. Dalton's got it right. So he's saying that it's going to be 4 times as much force. And that's right, because if you double the diameter, then that's 4 times as much area, because pi d squared divided by 4. So if you go through the numbers here, you know, back to the example, all right, so the area to begin with was 0.049. Let me get my calculator out here. So now if it's 0.5 squared, 0.5 squared times pi divided by 4. So now the area is going to be 0.196 instead of 0.049. So that's 4 times as much area. And so it's kind of an interesting thing that you can suddenly have, without changing the compressor, you can have the same compressor, but if it acts over a larger area, suddenly it's going to cause a larger force. And so this is a way to, it's in effect a form of mechanical advantage. Similar to using levers, you can have a really strong lifting capability by having the pressure act over a larger area. They do the same thing with hovercrafts. By having a big area on the bottom of a hovercraft, it's able to lift something very heavy. Later in the semester, we'll take a look at a hovercraft that's operated by the Navy and see what kind of lift capacity it must have based on the pressure that's underneath the air skirt of that hovercraft. So the idea here is force is pressure times area. So let's consider the case of a hydraulic jack. And this hydraulic jack is kind of complicated. This is one of those examples where, boy, I really wish we were in the classroom together, because this is one where I need to be looking at you and seeing who's got the ideas, who's struggling with the idea, And it's really useful in situations like this to pair up with another student and get into groups and talk about what's happening. But let's talk through this together as best we can. If here at location F, on the handle, we're applying a force of 100 newtons, then how much can be supported by the jack? So what is the magnitude of F2? Now, we kind of already guessed that the purpose of this is to lift something heavier than you could support with just your hand. So, logic would dictate it's going to be more than 100 newtons. But let's just go beyond that and see why it might be even more. So think about what's happening when you press down on the handle. That's going to be pressurizing the oil, the hydraulic oil that's inside of this jack. We don't know what the oil is, but it doesn't matter. It could be some motor oil, it could be hydraulic fluid, it could be water, and it would still have the same effect. The pressure transmission is independent of which fluid it is. When you press down on the handle, it's pressurizing the fluid because a force is being exerted over an area. You can see that here they're calling that A1. There's a certain area, this plunger, it's kind of like a piston where the force is being applied. So when you press down on F, what happens is that at B, there's a force that's going to be going down as well. And because of that lever length, however much you push down, on the handle, it's actually going to be quite a bit more at location B. And so there is the moment that's causing that first mechanical advantage. And so when we go through the calculations here, what we're going to see is, first of all, the first way that the force is being amplified is the longer the lever, the more you're going to be able to crank down at location B. And this is the same idea if you are trying to get the wheels off of a car. If you have a really long handle on the wrench that you're using, if you're using a breaker bar, they're sometimes really comically long. What you're trying to do is cause a really large force. And so we're amplifying the force. And so we push down with 100. There's going to be more than 100 acting down at location B. And so the magnitude of that force divided by whatever the area at 1 is now pressurizing the fluid. So the fluid inside here is pressurized. And they're at about the same height, so we don't have to worry about if the pressure acting on surface A1 is different than the pressure acting on surface A2. We'll assume that those two pressures are the same. So now, though, you'll notice that A2 is bigger because the cylinder at B has a diameter of 1.5 centimeters, but the cylinder that the F2 is being applied, it's 5 centimeters diameter. So larger diameter means bigger area. And so whatever that pressure is now acting over a larger area, so it's going to be an even larger force. All right, so I'm going to pause here. Now, we've still got 35 minutes until we're out of time for class. And we're going to use a lot of it on this example because I don't want this to be one of those cases where we rush through it and I just show you the solution. I really want you to chew through this and try and figure it out step by step. So as you get certain things calculated, let me just kind of give you the overview of the step by step. Okay, first of all, find, if you're taking a bulleted list, part 1 is find out what is the force acting at B. And you're going to do that through moment analysis. Then find the pressure in the fluid, because you're going to know a force and you can calculate the area. And I'll type the area for the formula for area on the screen. I think I've mentioned a couple times already, but I'll put it up there just so you've got it. So you'll know the pressure, and then find the pressure acting over this other area, how much force it can lift. All right, so begin your calculations while I type in the area formula for a given diameter. All right, so just the first part is the moment analysis to find out what's the force at location B. And so here's the setup for that. We have this handle, and the point of application for the force is 33 centimeters away from the axis of rotation. So it's rotating about C. That means that the moment distance is going to be 33 centimeters. And then for the opposite reaction, F sub B, we don't know the magnitude of it, but we do know its location is 3 centimeters away. Okay, and so that means that the force is going to be 1100 newtons. So F sub B, the magnitude of that force is 1100 newtons just because of this moment analysis. If we're pressing down on the handle with 100, it's further away from C than this other force is. And so to counterbalance it, the product of the force and the distance have to be equal. When this is in equilibrium and it's not rotating, since the 100 Newton force is further away, F sub B has to be larger. All right, so that tells us what the force is. And so it's that force that's being applied over this area 1. And so what you need to do now in the next step is, first of all, calculate what is A1. What is that? And calculate it in meters. Even though its dimensions are described in centimeters, you should calculate how many meters is area 1. And then from that, you can calculate what's the pressure in the fluid, because the force is 1100 newtons, and it's being spread out over an area that you'll calculate with pi d squared divided by 4. All right, let me bring it up. This next step. All right, so we know the force at B and the area of that part given its diameter. So the diameter is 1.5 centimeters, so that's 0.015 meters. We square it, multiply by pi, divide by 4. So now we've got the area in meters, and then we want to find out what's the pressure. So it's the pressure on the bottom is going to be the force acting over that area. So 6,225,000 pascals. Okay, now the next step is similar to what we've done already. The next step is we're going to say that's the pressure of the fluid inside of this device. Inside the jack, we know it's 6.2 megapascals. And so that's going to be the same pressure that's acting on this A2. And so it's pushing up on A2. And now find the force. So force is pressure times area. So again, you'll need to calculate the area from the given diameter. So find out what is A2 based on 5 centimeter diameter, and then force is pressure times area. All right, so for a 5 centimeter diameter, can see we have pi d squared divided by 4. It looks like I got it wrong the first time. I was missing a 0, so it can happen to everyone. So with that area, and now I know the pressure, so force is pressure times area. So it is a pressure acting upward in the magnitude of 6 megapascals on an area of 0.0196 square meters. And so the magnitude of the force, the jack can lift 12,222 newtons. So it's using pressure transmission and mechanical advantage to make it possible to lift quite a lot more than just an ordinary hand would be able to lift on its own. All right. Before we move further, any questions on this example?
Can you show the work for the torque again? I think I missed a part.
Sure, I'll bring it right back up. Let's see if I can get the whole example in one view here. All right, there it is.
Okay, thank you.
Sure. Yeah, the dimensioning is a bit small there, but the thing to keep in mind is that if we're rotating about C, then the total distance from C to the point of application of this hand force is 33 centimeters. And then the opposing direction, the clockwise rotation, that applicable moment distance is only 3 centimeters. So we have on the one side 100 newtons, which is causing a counterclockwise rotation, acting at 33 centimeters, and that's resisted by force B at a distance of 3 centimeters. Are there other questions? If I'm not mistaken, you'll get a chance to practice this again on the homework assignment. Let's just see what that problem looks like. Oh boy, some familiar stuff. Okay, we've got another jack problem. That's right like the example, isn't it? This one though, the guy standing on the platform, you haven't seen that exact setup before. I won't spoil it for you, but then, you know, another jack, and it's describing a mass that's hanging from the handle. And of course, you know, to convert between mass and force, the difference there is that you multiply by G. So if you want to find out how many newtons that mass that's hanging from the handle exerts on the handle, then it would be 25 kilograms multiplied by 9.81 meters per second squared. But yeah, the point is you do have some opportunities to practice these ideas in the homework. All right. Now, measuring pressure can be accomplished a variety of different ways. And one of the simplest ways to measure pressure is with a device called a manometer. A manometer, like is shown here, a piezometer, measures the pressure inside of a pipe by simply puncturing the pipe and then having a tube leading upward from it. And so let's just try and envision, what if what's being illustrated here is a water pipe that goes down the middle of the road, and it's taking water from the treatment plant towards people's homes. If you wanted to know what's the pressure of water inside of that pipe, one way to measure it is to have this tube going upward, and then the water will rise to a certain elevation as an indication of how much pressure is in the pipe. So if you have just a little bit of pressure in the pipe, then the water level would just rise a little. If you have a lot of pressure in the pipe, then the water level is going to rise to a certain elevation, and then it's going to stop. Now, it's possible that if this confining piezometer tube, if it's not tall enough and you have a lot of pressure in the pipe, then water could spill out the top. This is open to the atmosphere, this piezometer. By definition, it's not enclosed. And so one of the weaknesses with this way of measuring fluid pressure is that it only works for liquids. It doesn't work for a gas because the gas would just escape out into the atmosphere. But here in the blue italics it says if H is 10 meters, then what is the pressure at the center of the pipe? So you can use the hydrostatic equation to calculate the pressure at the center of the pipe. And earlier I said that sometimes we use pressure head as a way of quantifying the amount of pressure. And this is one of those cases where it's called the pressure head, the height to which water will rise in a static tube. Even if the water's flowing through this pipe and it's not static, conditions inside of the piezometer tube are static. And so the hydrostatic equation will apply for what's happening inside of this piezometer tube. So we can use the formula of delta P is delta H times gamma. And so if you have your calculator handy there, we can find out the pressure inside the center of the pipe because we'd have 10 meters, multiply it by 9810, and so that's 98,100 pascals. So think about if you were going to try and measure the pressure of water in a municipal network with piezometers like this, rather than using pressure transducers or some other method. If you only had access to a piezometer, then the range of pressure inside of a municipal network is between 240 kilopascals up to as high as 850 kilopascals. So what that would mean is if you're going to be measuring 850 kilopascals, then you'd potentially need to have a column of water 86 meters tall. So it's not really a practical way of measuring pressure out in the real world. You wouldn't use it for a variety of reasons. Since it's open to the atmosphere, then that means that the water could become contaminated with whatever's in the atmosphere, whether it's pollution or particles falling in, a bird flying overhead. So it wouldn't be sanitary, but it's also not practical because the water height would be 86 meters, and so that's nearly the length of a football field vertically. And so it's important for us to know what piezometers are, and we're going to use these in the lab later in the semester. We will use piezometers in order to measure the pressure inside of the venturi. When we do the Bernoulli lab, then we're going to actually see the pressure change through the throat of a venturi, and we're going to measure the magnitude of that pressure change with a piezometer, very similar to this. But it's just one of the simplest ways for us to quantify pressure change. So for high pressures, it's not practical because the H just gets so tall, and it's also useless for gases because the gas would escape out the top and go into the atmosphere. So we're going to continue talking about different ways to measure pressure with manometers when we continue on Thursday. Now, most of you are in the civil engineering lab. That is today, and that is the hydrostatic equation and hydrostatic forces. The lab handout is available right now on the class webpage, and so I'd encourage you to look through it between the time between now and lab. You either have lab today or tomorrow. I've printed out a copy, so you don't necessarily need to print your own. I'll have one for you. But I'll also renew the invitation if there are any mechanical engineering students who are available and interested to come see the lab. We'd be glad to have you join us. It's at 2 o'clock and at 3 o'clock today and tomorrow. And the room location is room 1228 here in the Applied Engineering Complex. So You're welcome to attend. Of course, it's not required. It's only for the civil engineering students who are taking CE 319. But it'll be helpful to actually see the effect of hydrostatic forces. Before we go our separate ways, let's just take one final look at these announcements. Remember that homework 2 is due on Thursday, and I'd encourage you to look through the comments that the homework grader has taken the time to put into Blackboard. So homework 1 is finished grading. So your score is available, and you can look through what the grader told you. And also, I've put the sample exam and the equation sheet on there. If you have any concerns with the grading this semester, feel free to let me know. I think that you're very fortunate to have a very knowledgeable and thorough and careful grader, but everyone makes mistakes occasionally. So if you think the grader has misinterpreted something that you wrote, or if you think you got it right, but you got the points taken off, if there's a problem like that, just let me know, because I want everyone to get the points that they deserve. So otherwise, that's it for today. I will see you in our lecture on Thursday, if not before, in the lab on Tuesday or Wednesday. All right, Jeremy, you have a question.